Good morning, good afternoon, or good evening, whatever time you're watching this another educational video. And this moment we will be discussing about Universal Law of Gravitation, of course, by Sir Isaac Newton. We will be talking about the concept here about this universal law from the word itself, universal. So this is true everywhere in the universe. But before anything else, do not forget to, of course, subscribe to this channel. Thank you. This law states that any two objects in the universe that possess mass will exert a mutual gravitational force of attraction on one another. Gravitational force is always attracts. It always attracts masses between their center, not the surface of the mass or the masses itself. Okay, so it exists between the two objects and they will share the same or mutual gravitational force. That's the law, the universal law of gravitation. Now let's talk about the formula as to how to get the gravitational force being exerted both mutually by the two objects. So our gravitational force is just Fg is equal to like this big G. We will be, or this uppercase G, we will know it later on. We have, of course, since it deals with two masses, so we'll have one or mass 1 and then mass 2, and we will divide it by the radius r squared. Okay, that's pretty simple. We can get the Fg, or the gravitational force between objects or between masses, by just simply following this equation here. So let's talk about the variables one by one. The first we will discuss about Fg. Fg is the gravitational force between the centers of the two masses. It should be measured, of course, in meters. So if you will have in the given, you will have centimeters, convert it to meters by just dividing it by 100. And remember, gravitational force between the centers of the two masses. So I just want to draw it here. Let's say let's have mass 1 and then mass 2. The gravitational force between the centers of the two masses, we can let's say this is the center of our two masses here. So the gravitational force, we can say the force of mass 2 is pulling mass 1 towards it. Okay, and then force of mass 1 is pulling mass 2 mutually with the same gravitational force towards it. So it's opposite. In this case, it's going to be the positive value of the Fg and the negative value of the Fg, or the gravitational force. Keep that in mind. It should be from the center, from the centers of these two masses, not this way. Let's say um, the force is here and then here. Always remember that we will follow the definition. It must be from the centers of the two masses. So definitely we have to stretch it out here, centers. Okay, and the directions of the arrows, positive and then negative, because force is a vector. Gravitational force is a vector, so we have to keep using the negative and positive here to be our sign convention for this concept. Again, I will write the formula Fg. We're done discussing the gravitational force. We have the capital G, mass 1 times mass 2 over the r squared. So let's have to deal with G. So what G means? The uppercase G, or the caps lock G, it represents the universal gravitational constant. So from the word itself, universal. So for sure, it is true anywhere in the universe. And yeah, it's here. Unlike the local gravity, like on Earth, our gravitational pull, or yeah, gravitational pull is 9.8 meter per second squared. And in some other celestial bodies, they will have their own gravitational or local gravitational pull. But yeah, unlike local gravity, this G is exact same everywhere in the universe. Like what I have said, universally. So it's used uh, as a universal value, or it's constant in any part of the universe. But yeah, the value is very small. It's incredibly very small value, and I'm gonna give you what's the this constant, this universal constant. Note G is equal to 6.674 times 10 raised to 11, and the unit is Newton meter squared kilogram squared. We have Newton meter kilogram squared. That's the unit of our gravitational constant, or universal gravitational constant. Again and again, I want you to somehow familiarize this figure here. This constant, 6.674 times 10 raised to negative 11 Newton meter squared kilogram squared. And yeah, we have mass of one object here and another mass of another object, since a mutual attraction between two masses. Okay, and we have the radius r, that's the distance, and it must be in meters as well. Right, let's talk about inverse square law. Again, it's inverse square law. From the word itself, inverse, we flip it, we do the reciprocal of it. And this inverse square law, a lot of learners will get wrong answers with regard to this law. It just asks this question, like how does changing the distance r, how does the distance r, or the mass affect the gravitational force, or the Fg? How does r and the mass affect the gravitational force? All right, we will try to compare the relationship between the force and the distance r. And as we all know, Fg is proportional to the radius r. Okay, and if you notice, we have to know that it also have over one there to match with our fraction here. Okay, and if you notice, f is in the numerator and r is in the denominator. They are like opposite in our fraction. So we can say that it's inversely proportional. Their relationship between the distance and the force is inversely proportional. Meaning to say, if ever that our radius will become higher and higher, or larger and larger, it will have an opposite or an inverse effect to our force, gravitational force. It will become weaker and weaker. If ever we will have a shorter radius, it will become shorter and shorter. Our force, a gravitational force, will become stronger and stronger. So that's inverse, the opposite. And if we will try to know the relationship between the force and the mass, if you notice, we have mass 1 and mass 2 here in our formula, right? It's in the numerator and numerator. Understood, it will have over 1 there. So if they are located in numerator and numerator, the relationship will be directly proportional. Meaning to say, when we have directly proportional relationship between the force and the masses. If we have heavier masses of the two objects, so we'll have stronger force, gravitational force. If we have a lighter or not so heavy object, so our force will also be decreasing. Okay, remember Fg and R, the distance and the force, it's inversely proportional. But force and the masses, it's directly proportional. Now, I have here the distance factor. What will happen to the force factor if we will try to double the distance r? The distance factor will be 2, and then we will cut the distance into half, so it's going to be 1/2 as our distance factor. Or what if we will triple the force, or even we will make it times 5? What will happen to our force factor? So let's begin. Always remember Fg is the Fg is proportional to 1 over r squared. So what will happen here if we will double the distance? So this is what will happen. So 1, we will place 2 here since we double the distance, and then squared. In that case, it will become 1, 2 times 2, that's 4. Okay, and if we want to get the force factor, we have to divide 1 by 4, and remember we have over 1 here. So in doing so, we will divide 1 1 and then divided by, so we will make it positive in dividing fractions, and we will have the reciprocal of it. I mean, we will flip the values. So 4 will be in the denominator and 1 will be in the numerator. So 1 times 1, that's 1, and then it will have over 1 here, obviously. So 1 times 4, it's 4. So the factor will be 1, 4. If we will double the distance, the force will have a factor of 1/4. So what about if we will try to cut distance into half? 1 over, that's 1/2, and don't forget to square it out. So 1 over 1 times 1, that's 1. 2 times 2, it's 4. So we will divide 1 and then divide, make it a multiplication, and then the reciprocal of it. Just flip the values. So 4 will be over here, and then 1 will be there. So 1 times 4, that's 4 over 1 times 1, that's 1, or simply 4 divided by 1 is 4. So the factor, if we will cut the distance into half, we will have a force factor. And what about we will triple we will triple the distance? So 1 over 3 squared, that's 1 over 9. Then, of course, as I said, it will have 1 here. So we will try to divide fractions now. 1 divided by, so make it multiplication, and the inverse of it. So 1 over 9. 1 times 1, that's 1. Then we have over 1 here. 1 times 9 is 9. So this is the force factor if we will triple the distance r. What if we will multiply? I will just put it there. 1 over 9 as the force factor if we will triple the distance r. Now, what about times 5? So 1 over 5 squared, that's 1 over 25. 5 times 5, that's 25. And we have over 1 there. In dividing fractions, all you have to do is to divide it 1 over, or let's say 1 multiplied by the reciprocal of this. Just flip 1 over 25. So the answer, 1 times 1, it's 1. And then we have 1 here. 1 times 25, it's 25. So this is going to be the force factor if ever the distance will be 5 times. Okay, so 2, if we double the distance, we will have a factor of 1/4. If we will reduce it to 1/2, so we'll have 4 force factor. And we will triple the distance, we'll have 1/9 force factor. And 5 times will become 1, we'll have 1/25 force factor. So let's have a problem here. The gravitational force between two planets is initially 120. That's the initial, or we can say that's the old, because we will gonna find out what will be the new gravitational force here in this problem. If the distance between the centers of the planets, they never put the masses here, so we will do the shortcut thing, is being tripled. As we all know, if it is being tripled, our force factor will become 1/9. So let's figure out the new gravitational force. So we will equate, let's say, look at this one. Old, this is the old gravitational force. So it will have a formula of, as we know, G m1 m2 over r squared. So this is going to be the old radius of force, since we need to triple it out. So in this case, we can say that um, we need to find the new gravitational force here. So since these masses are not included, so we can just simply say that uh, f g new is equal to the f old, and that f old here constitute this value. It's inside this variable, the fg old. Okay, and we will try to remember, if we triple the the distance, our force factor will just be 1/9. We just calculated it a while ago. So in this case, we can just simply say that the old fg value is 120, initially 120. So we can have 120 here, 120 newtons. And of course, we have our force factor if we triple the force. So it's going to be 19. We just have to do it like this, and then 120 times 1, that's 120 over 9, or it is equivalent to, we will try to solve it using our calculator. So 120 divided by 9, the answer will be 13. 13.33 is the new FG. As we all know, FG is inversely proportional with our R squared. So we increase the R squared, so we will have to have a lesser FG here. So yeah, this is it. As simple as this. If the problem will not give you the masses, the value of the two masses, and then of course we can just do the shortcut by knowing the new gravitational force, by just multiplying if ever it will be tripled, or 5 times, or in this problem it's tripled. So as we calculated earlier, the old fg, you can just multiply it by the force factor if the distance is being tripled. So that's 1/9. Okay, if the distance is 3, we have a force factor of 19. So just uh disregard the units here, but in your final answer, don't forget to put the unit, just like this one. The answer is, I will make it clear, it's 13.33, and the unit will be newtons. Okay, so it makes sense because our radius r is getting larger 3 times, so it goes up. We'll have a weaker new gravitational force from 120. Imagine it becomes 13.33. I hope you learned something from this video. Please make sure that you will study this one before your term examination. Thank you so much and see you until next time. Bye for now.